back. Could you stand close to Andreas?
Oh, sure. Yeah, no problem. Okay, well, I guess we'll go ahead and start. Unfortunately, Michael couldn't be here today. Hopefully, he'll be back to campus in the next week or two. But I'm very happy to get the chance to introduce Andreas Noack, who finished his PhD in economics midway through 2014 at the University of Copenhagen. He did a very brief stint at Oxford, and then he moved to MIT in August of 2014 and has been in their Department of Computer Science as a postdoctoral researcher with Alan Edelman since. And so what he's going to talk about today is dense linear algebra, or linear algebra in Julia, and all of the work that he's done on that since he started his postdoc. So I'll go ahead and let him take over.
Thank you very much, and thank you for showing up. It's a big honor to be here at Stanford talking to you. As Jack told me, and first of all, I should say thanks to Jack for actually inviting us here to Stanford. It's been a pleasure to be here in this week. As he said, I will talk about linear algebra in Julia because that's what I know something about, because I've implemented quite a few of the routines and been quite much involved in how it's actually set up. And not just since I started as a postdoc, but actually also while I was a PhD student. And it was kind of the reason why I ended up in Cambridge, Massachusetts. The outline of my talk today is the following. Hopefully it's not too small. I'll start to tell you a little bit about what is Julia. I don't know really how well known Julia is here. Probably you've heard of it, but I'm not sure how many of you has actually, let me see, how many has actually tried Julia at all? Okay, and how many are using Julia regularly? Okay, that's fine, I think. So I'll give a little bit background about Julia, who is behind it, and then I'll tell you about what I think the main new thing or the main benefit of Julia is, and hopefully I can give examples afterwards that will actually convince you that Julia is useful. So the subparts of that argument is first I'll give some basic introduction to how is the syntax of linear algebra in Julia, and it will be very basic. I'll try to use quite simple examples because it's not the models as such or the linear algebra concepts as such I would like to focus on. It's more how we express them in Julia and how you might be able to use Julia and the concepts in Julia to express what you're doing. So the examples are very simple. So I'll go through our different linear algebra the types and concepts in Julia. Then I'll talk about how this makes it possible to use linear algebra in Julia for quite generic data types, such that you're not just restricted to the usual floating point representation of numbers. That's a thing I've been spending quite some time on. Then I will try to argue that Julia is actually fast, and actually fast enough to compete with more lower level, high level languages that are usually used for actually writing numerical libraries. And finally, I will briefly touch upon what about parallel computing in Julia. So first, what is Julia? Julia is fast and Julia is easy. Hopefully that is the two things that you will remember after this, or that what I hope to achieve. If nothing else from this, that you actually believe this. But the real way to figure this out is to use it. But hopefully I can make you convinced that you should try it. So first, who is Julia? So this picture, I found that by Googling Julia Lang. So this is Kayan, and the four others are the founders of Julia. It is Alan Edelman to the right, and then Stefan and Jeff and Riel. And they created Julia. I think they started back in 2010, approximately. And it was publicly released on GitHub in the beginning of 2012. And I found the existence of Julia a little bit later that year. But all what I've been doing is built on the works of these people. Actually, all of them somehow. So I owe them a lot of thanks because, yeah, all what I'm doing now is based on their work. But beyond that, as I said, Julia was made public available in 2012. And since then, the number of contributors has risen quite significantly. And as of this Friday night, it was 348 registered contributors on Julia. And thanks to Jiao, who's sitting there, I have this map here where the red dots shows where the contributions are made from geographically, kind of. So you can see it's very much a European American thing, but we also have quite a significant contribution, from Bangalore. But it is we have activity from almost all over the world now. I should also say that if you have questions, please ask along the way. So beyond the contributions mapped in the world map here are to the base library. And beyond the base library, there is quite a few packages now. This graph here, this is due to Ian Donning from the Department of Operational Research at MIT. He's managing he's tracking all the packages. So this is the last year where you can see the development in the number of packages, and different colors are the number of packages supported by different versions of Julia. So back a year ago, the main release version of Julia was 0.2, and then here in the summer we released 0.3, and you can see the packages for 0.2 were discontinued. And now most packages are developed for the release version and the development version. And we don't know for sure, but hopefully in the summer there will be a new release of Julia, the 0.4 release. But there has been a steady growth in the number of packages. So I think, and when I talk to people who started to use Julia, I think that the main difference that people feel after working with the language for a while is that it, to a large extent, solves the two-language problem. It is not necessary, it is rarely necessary, I should say maybe, that you have to move core parts of your numerical code outside the language. So it is very common right now, if you work in MATLAB or Python or R, that you develop some code that is actually working in the convenient language, figure out which part is not fast enough, and port that to Fortran and C or C. In Julia, that is not really the case. And one plot I like that illustrates the combination of convenience and speed is this one, where we have a collection of micro benchmarks in our repository, and of course they are always you can always discuss how representative are they for real code. But anyway, we have a collection of these micro benchmarks, and on the second axis you can see how long does it take to run them. For different languages, they are quite small, but I can point to which languages are which. And then on the first axis, you have an indication of how many lines does it take to implement the benchmark. So up here, you have Octave, and you have MATLAB here. Here you have Python. Down here you have C, and I think that's this JavaScript. And down here, to the bottom left, you have Julia. So you can actually write quite compact code, and it is also almost as fast as C for the micro benchmarks. You can say that they are not fair in some sense, but I think this is also the feeling of many Julia users, that they are able to write compact code that is still okay to read and executes quite fast. So that is the main story about Julia. And one of the 2 points I would like to make today, that Julia is fast and convenient. But the other main point is that it's also very neat for expressing your ideas as sign systems. The type system in Julia is actually I have found very fun to try to express different ideas and try to make it fit into the type system. And I'll give examples of that later on. So to kick it off, let's look at some code. So these are 2 examples I like that shows simple ideas used in the language, or simple syntax that can with different aspects of the syntax. So much of it looks like MATLAB, as you know it, but there are some more. You can see if you take the first line here, we are producing a matrix 3 by 3, piping into an anonymous function to make a symmetric matrix in one line, very convenient. And we can use we have quite extensive Unicode support, so if you want eigenvalues to be lambda, they can be lambda. Furthermore, we have an I that is a generic identity, so you can just write lambda I as you would do in math, and then the I is a generic identity and it figures out how large am I, so I don't have to produce an I matrix in the same way I would do in MATLAB. And I avoid allocating a huge matrix just to have an identity matrix. The second example is that if I want to define a very simple function, say the Fibonacci function, then I can make a one-liner like this. So I simply ask, is the input n smaller than 2, then return 1, or if not, return the sum of the 2 last recurrences parts. And I can easily print that with string interpolation, printing the loop variable and the result of applying the function to the loop variable. So if I apply this, I get this printout. These are 2 very simple examples of the syntax of Julia, and which kind of exemplifies why I can write fairly compact code. So, so far so good. I'll browse through some basic steps of the syntax of general linear algebra now, and it is very basic. It's just so that you actually know how it's structured. So, as I said before, a matrix of random Gaussians can be produced in the same way as MATLAB. What I would like you to see here is that when it's printed, it starts with printing the type of the object. So it's an array, and then there are 2 parameters of the type. It is a float 64, and then there's a 2. So the type has 2 parameters, one specifying what are the elements of the array. So all arrays in Julia has this type specifying what is actually the content of the array. And the second one is the dimension of the array. So if I produce a vector of 1s, the second number is a 1 here. So, and you can have arbitrary dimensional arrays in Julia. There's no hard limit there. But at some point, you probably would like to stop. And as it is the case in MATLAB, you have simple multiplication. You can add the transpose. You can do the inner product or the matrix product with a prime to produce a positive definite matrix. You have matrix solve with a backslash, and you can solve least squares problems. So if you extract 2 columns, you get a thin matrix, then it's automatically, as in MATLAB, it is a least squares solution. You get some regularization for free. Where are we? Here. If I take the first column of A twice, then automatically you get the solution. There are, as you know, more than one solution. You get the one with the minimum norm. And this is, of course, just exploiting what we have available in LAPACK in the same way as other high-level languages use what's available in LAPACK. But we have the same. So much of internally how this is structured is through the use of factorizations. So we have these types in Julia that we can use for expressing these different linear algebra concepts. So we have an abstract type in Julia that is just some kind of factorization that represents some form of a matrix. So a factorization is some representation of the original matrix that is not just the elements stored as in the original matrix. So for instance, it could be in the LU factorization. So if you write LU fact of A, the result is a LU type, which again has some parameters. So underneath, it's still just a matrix, which is printed here, and some pivoting information and a number saying, okay, this factorization went well doing the LAPACK call. But besides that, it is stored in an LU type, which we can use further on when we are working with this factorization. So, for instance, we have fancy indexing of such a type. So we can do indexing with symbol P to get out the pivoting matrix. And we can do index with L to get the L part, and U to get the U part. But internally, it is just the matrix stored, and for you familiar with the LAPACK, it is just such that the strictly lower part is the L part with the implicit assumption of the ones, and the upper part is the U part. That with the fancy indexing, of course, you can solve a linear system of equations as in the textbook, but you would never like to do that in practice. You would like to use the factorization. So the backslash, as in many of the other basic arithmetic operators in Julia, are heavily overloaded. In particular here, it's overloaded to take a LU factorization and some kind of vector to produce the solution of a linear set of equations. So internally, if you have a square matrix and use the backslash, what is actually happening is Julia checks what's the shape of the matrix. Okay, it is square. Then it's factorized with this LU fact, just as I did here, and then it's calling the specialized backslash for LU factorizations. So you can use that yourself, and it is also the way we structure all the code inside. Use these factorizations. First, make a runtime check of a matrix. What's the shape? What's the properties? I'll show some more examples now. And then use the specialized functions afterwards. But the user can also directly say, I want the LU in this case. I don't want Julia to analyze the matrix at runtime and decide how to factorize it. So one other example is if you take the determinant, then of course you would need to do something. You can not just have a large matrix and calculate the determinant directly. So the usual case here, and the way we're doing it is use the LU factorization and use the product of the diagonal of the U and then design the sign for the permutation. So that's also how it happens behind the scenes. We are using the factorization object. So next factorization showing this is the QR. As you are all very familiar with, convenient for the least squares problem. So when I'm QR factorizing, in this case a tall matrix, I take A is still 3 by 3, so I'm taking the first two columns. Then I'm getting the way that I'm getting a type that represents the way LAPACK works with the QR factorizations. So we have a part containing the R part and the householder reflectors in one matrix. And then we have the loadings of the reflectors for you who are aware of how they work. So, but again, the main thing here is that we have information about we can use the information that it is a specific type, the QR type, to overload the backslash, such that if you have a QR factorization of a tall matrix and apply backslash to that and some vector, then what is actually happening is that a least squares problem is solved. So backslash in this case is overloaded to produce the least squares solution. This is not how Julia solves the problem for a general tall matrix, because we default to use a pivoted QR such that we can actually use regularization. So it's just to say that we can turn on this is pivoting, the true statement here, and then we have a rank efficient problem, taking the QR factorization, and then we are able to solve a rank efficient problem, the same as I did initially without first QR factorizing the matrix. So again, this will be the thing that happens behind the scenes. If you put in a tall matrix, Julia will say, okay, first dimension larger than second dimension, let's do a pivoted QR, then call the specific or the specialized QR backslash method on that factorization. So here's one of the neat things about this, because Q is an orthogonal, or in the complex case, unitary matrix, which can be represented by less elements than the n square, for instance, if the original matrix is n by n, or less than n by n elements if it's a tall matrix. So we only need the strictly lower triangular part of the matrix to store the reflectors. And we're actually only using that. And then we can make Q behave as if it is the full square Q part, or it's the thin Q part, because that doesn't really matter when you're applying householder reflectors to any vector or matrix. So just to give an example of how this works, if we have made a QR factorization of a vector length of the A matrix, and then we can apply multiplication to a vector of length 2, but we can also multiply with a vector of length 3. So the context decides how should Q be interpreted. Is it only, or is it only the orthogonal basis of the columns of A, or is it also the Q1 part for the space orthogonal to the column space of A? So the context can decide, and if it doesn't make sense, you get an error. So, but of course, if you could be unlucky that it will actually confuse you. So some people don't like this behavior, some find it too cute, but I like it. So finally, I'll briefly just say that we have a similar way of wrapping the result of eigenvalues, so that you can, if you happen to have eigenfactorized a matrix, then you have a very fast way to get the inverse, of course, as your first course in linear algebra has taught you. That is, of course, not efficient if you have your matrix in the original format, but if you happen to have it eigenfactorized already, then it's a very efficient way to get the inverse. Or alternatively, down here, if you take an SVD, we have overloaded the backslash of the SVD, so you can get a least square solution based on the SVD instead of the pivoted QR. So you say, I want to solve this least squares problem with the SVD because I believe that is more precise, so that's just better, or I would like to use the SVD for that. I just make Julia do that by explicitly SVD factorizing my design matrix and then applying the factorization with backslash to B. Short story about sparse factorizations. What I will mainly point out here is that they exist. So you can do LU, Cholesky factors, LDLT, and QR factorizations of sparse matrices as well. So you can solve least squares problems, you can solve underdetermined problems, you can solve normal linear equations with sparse matrices as well. They are not as neat to work with. It is, you wouldn't usually want to extract the lower triangular part of these because they have very fancy and sophisticated storage behind the scenes. And basically, as you can see also from the way I've printed the different factorizations here, I've printed each of them. They are mainly they're just containers around pointers to Tim Davis's libraries for sparse matrices. I should say here at this point, if you are using Julia, you will see a big difference between 03, the current release, and 04, our development version, because I spent quite some time on working on this. So it is the sparse factorization are working much better in the release version. So you can look forward to that, or just use it, the development version.
What did you change?
I understood the libraries better, I would say. So, so it can be a little bit challenging to call Chalmot correctly, I think. And in the end, I figured out how to do that. So it was kind of inefficient in the way it called them earlier. Yeah. So, in particularly solving positive definite systems, I think. Another thing where we're exploiting the types in Julia is to have special matrix types. So, and we do that for two reasons. One of them is for efficient storage. So, for instance, we have a diagonal type, this guy here. So, even though it prints as if it is a normal dense matrix, internally what is stored is only the vector. So, we can save a lot of storage by doing this. But the second part is also that we can actually, because we now know it is a diagonal matrix, we can directly call into a efficient solver, for instance. So if we apply backslash to a diagonal matrix, it won't try to factorize the matrix first. It will simply just divide the rows or columns, depending on if you're right or left dividing with the diagonal. It will simply just scale the columns or rows. So, and it will not do any runtime check. It will just call the right function for actually applying a diagonal matrix division to the matrix. And that is the main reason why the lower triangle exists, because that is kind of the basic building block of numerical in algebra. So when you're applying a backslash to a triangular matrix, it calls directly into a back or forward substitution and will not try to factorize the matrix. So that is a way to tell Julia, go directly to the back or forward substitution. And similarly, we have symmetric and symmetric tridiagonal matrices for use for the eigenvalue case. So if you wrap a matrix in a symmetric type, Julia would not try to figure out is this matrix symmetric or not. It will simply just look at either the lower or the upper triangle, and by default it's the upper, but you can ask it to look at the lower instead. And the symmetric tridiagonal is only storing the diagonal and the lower or upper subdiagonal. And to show how this can matter to you, I've taken a little bit larger problem here. So I'm making a symmetric 1000 by 1000 matrix here. And then what I'm doing at this step here is I'm destroying the symmetry of the copy a little bit. So I'm adding a little bit of noise. So as a result, when Julia tries at runtime to analyze the matrix, then it will come out as a non-symmetric matrix. So that's what I'm printing here. And checking is the matrix symmetric. And these guys here, I haven't wrapped in the symmetric type. That's the whole idea. Yeah?
Is there a built-in spell checker, grammar checker for the comment stuff? And for example, you've got detect rather than detect, and I instead of is, things like that?
No. Sorry for that. Nope. That's not in the IPython notebook, and I should be more careful.
The web browser might support it
though. Yeah. I can't promise that there won't be any more of those. Yes. So to see what difference it makes here, so Julia will try to runtime detect both of them here. Are they symmetric or are they not symmetric? And in the first case, it is perfect symmetric, and a LAPACK symmetric eigensolver is called. And in the second part, it is detected as not being symmetric, and therefore the general eigensolver is called. And you can see it makes a huge difference in the running time of the calculating the eigenvalues. So if you know for some reason that your problem is symmetric, you can exploit it. A typical example could be that you have some kind of quadratic form, say that you are multiplying A, multiply B, multiply A transpose, and B is symmetric, let's say positive definite. Then in practice, the result of this operation will in general not be symmetric in floating point arithmetic, because you start by multiplying A with B, and then you multiply the result of that with A transpose. And if you wrap that, so if you try to check for the values, it will not be symmetric, but then you can say, I know the structure of this problem, so I wrap it in a symmetric type, and Julia will handle it as a symmetric matrix. And the storage part of this, and also efficiency of computation. Here is an example of calculating the extremal eigenvalues of the Hermite ensemble. So usually you would have to match this, you would have to take a 1 million by 1 million Gaussian random matrix and then add its transpose and calculate the eigenvalues of that. That is too large to handle on my computer, but you can analytically derive that you can just construct a symmetric tridiagonal with random elements in the diagonal and chi distributed random matrix, random variables in the off diagonal instead. And in this case, and because of this, we can actually produce a 1 million by 1 million random matrix. And within 1.2 seconds, we can get the two extremal eigenvalues. So that's the lower part and the upper part of the semicircle.
So I kind of lost that. Did you actually allocate the matrix or what?
Yeah.
On your desktop?
Yeah. I did.
Let's try diagonal.
So I'm only storing the diagonal and the off diagonal. Yeah. So, any questions so far? Yeah.
All these packages you use, I mean, under what license? I mean, you're using your LAPACK like Tim Davis and other people, right?
Yeah.
Are they? I mean, I'm just curious. How do you resolve the license issue where you use so many other packages for other people?
So far here, I'm using 3 packages, right? I'm using LAPACK and OpenBLAS, which you didn't see, and then Tim Davis packages, kind of. So the Tim Davis part makes it LP, what it's called, GNU. Sorry? GPL. Yeah, GPL license. So if you want to have a completely free version of Julia, you would have to turn off that part of Julia.
Okay. So in the future, for example, MATLAB has all these spline packages written by Algebra a long time ago.
Mm-hmm.
And if in the future Julia wants something which is really like MATLAB, you can use all these packages. I mean, I mean, does that mean that I have to, I mean, is it going to be eventually going to buy a Julia package and use them? Or I'm trying to understand what kind of, I mean, Julia, the way you present it is like a free language which everyone can use. But when you actually try to use these functionalities, you have these legal issues about what package is free, what is not. I mean, how is that going to work eventually? It's like when you install it, then, but if you don't pay, then all these packages are going to be disabled, and you can't use it?
No, you can see what is it enabled just by default by downloading here. So all this will just be enabled if you download our version from the site, and then eventually in the future we'll probably solve this by having packages with more restriction licenses in add-on packages. So you can per package determine will I want to have this more restricted version of Julia. So the base library will be very free.
And you will pay these two from, how are you going to organize the pay structure of these things?
That we will not do any of that. So people, companies can organize that if they want to, but we will not take any money for that. So.
But if I download your package and I want to use it, who should I pay to then? Should I pay to Tim Davis, for example, or just Tim?
No, because
It's a very concrete problem.
you want to use, but because you want to use it for commercial use.
No, I mean, suppose Julia used someone's package. But I downloaded Julia, you said that if I want to use it, I have to pay.
No, only if you want to like sell a program with closed source software, do you ever have to think about paying for any of this? That's the only circumstance money would need to exchange hands, is if you want to sell a program and not let anybody see what you wrote. That's it.
You can use it for research and teaching, but it's only if you want to sell it.
But it's not good for the industry.
Then you would have to, but if it's an industrial application, they will probably be able to tell you which part you can use.
But then the question of whether payment comes up. If the company wants to
Yeah, but most of the basic base library of Julia is completely free, can be used in most applications. But if you want to use it more in a commercial application, you would have to go through some of the packages and see if it's okay. That's an order.
So your MIT lawyers are not proud of
No.
Actually, we have talked to them. They specifically
So, but that's not a part I've been working much on other parts of the language. So,
the internet is free too.
so let me continue to the next topic here. The part about generically in algebra, because the way the types in Julia are made, and as I showed to you earlier, the matrices are parametric on the element type and the dimension. In particular here, what's interesting is the element type. So instead of being floating points or complex numbers, it could also be integers or rational numbers or quaternions or finite fields or whatever. In the operations with multiplications and solve and so forth, you can decide not to promote more than necessary. So if you multiply two matrices of integers, the result is also a matrix of integers because there's no need to promote the matrices for doing that operation. So another example is solving a linear system of equations with the rational A matrix. So here I'm setting up a rational matrix where I'm using a new library, by the way. Big int is an arbitrary precision integer package. We have our own factorization, LU factorization internally, because LAPACK is only for the 4 single and double precision, real and complex. But because we have our own, we can solve this problem. It is of course not as efficient as LAPACK's, but it doesn't really matter when we work with these custom element types. We cannot really expect to get a very high efficiency of a rational big int element type. But it can be convenient for some problems actually to be able to solve it in perfect precision or exact precision as a rational solution is in this case. Yeah?
So what part is the and what part is Julia? So this package is just doing the arithmetic and you were supplying the decomposition.
Yeah. So yeah, for each element, the arithmetic is in the bigger package. So and the factorization, the element factorization is our part.
So you could do like symbolic algebra.
And you will see that in
Interesting.
I'll skip that. Next one here is another case, just the famous one, useful for teaching floating points. So the Hilbert matrix is very ill-conditioned, but it doesn't matter if we are using exact arithmetic. We can calculate the inverse without sacrificing anything. So they are growing quite significantly. And we can easily show here that if we do the same inversion but convert the matrix to floating point numbers, double precision floating point numbers before, then if we take the norm of the distance between the two results, the infinity norm, then the error is quite significant. So that's just a consequence of floating point numbers made exemplified by this example. So you could alternatively use a arbitrary precision floating point library to avoid this, and you can see that for the same problem, by the way I should mention that it's only an 8x8 problem, it's not really large, we can solve that, but it will only help us for a short time period, because if we make a 30x30 matrix, it's completely off again. This is 2 times 10 to the power of 8. Another example of that you can just substitute the elements of the matrix. So an example of finite fields. So here is a very simple and primitive example of how you could express Galois fields in Julia. I'm no expert on that at all, so it's mainly just to express a new kind of element that for which you could do some linear algebra. So here we are defining a new numeric type, and we store internally the internal representation of the Galois field is just an integer in this case. And then we are creating a constructor here, so we are just taking the input and then modulus to the base number of the Galois field, which is a parameter to the new declared type. So the Galois field has a base number, which is called n here, and then some storage that we can decide on. It can be integer 64 or integer 32 or whatever. It's free in this description here. Then we have to set up a few conversion methods and a promotion rule if it meets some other data type. How should promotion be done? So if you do some arithmetic operation on integers in the Galois field, what should the result be? But it is only these lines of code here you would need to define to have a new user-defined type. So here I can instantiate it. I can say Galois field with base number 2 and input 11, and it gives me 1, which is the way I have chosen now to print the result of this. And I can, in these lines, define basic arithmetic, just show an example of Julia's meta-programming capabilities, which I will not go more into, but I can loop through the 3 basic arithmetic operations, plus, minus, and multiplication here, and then define the binary operations here by using the already existing plus, minus, and multiplication of the integers below, and then taking the modular operation afterwards. And it works. So that's it for actually having a new type that supports some operations. Then, of course, the inverse takes a little bit more effort, as you know. And then we also have division. So now we have the finite field for all the 4 basic operations. So
are these functions you wrote out, are these pre-compiled somehow? Or?
They are compiled the first time I run the code.
And it's compiled into what? Into binary on the machine, or compiled to some immediate
Can you make that statement precise?
Yeah, it compiles, it uses LD to JIT behind the scenes to compile a bunch of native assembly code. And he can actually show you the assembly code if he.
And I will. Let's look at some. Which jumping in forward now.
So then you can introspect the assembly code of any JIT compile function.
So we want to call this function, we will dynamically link this assembly code in the program and run it?
Yes.
I have a question. If the function is recursive call, how do you compile this? Is this compiled as the first call? Or
Yes. So we compile the first call and every successive call. Either if we can figure out the type, so we can statically inline the actual address of the function to call, or if it has to do a dynamic lookup, like a runtime type check to see like what's the argument to call some function, it will do that and then basically call a specialized function behind the scenes. Yeah, it's all transparent. So.
I remember MATLAB also do some pre-compilation as well, right? But I understand Julia is faster than MATLAB when it comes to function calls. Why is it able to be much faster?
I think you should just let it keep on going.
Yeah. So now we have a new type that then we would like to do some linear algebra on it. So here I define a matrix A with elements from this new Galois field, and I use just to make some. I make the base number 5 here. Let's do a 4x4 matrix. And I produce a right-hand side vector as well. So, and because we have defined the operations to support a field, and that is what we need to do in LU, we now, without any, oops, I need to run the code, sorry. There it is, sorry. So now I have defined A and B, and then because the elements of A support field operations, the LU works right away, and we can solve a linear system of equations. So that's the generic part of the algebra, and it is the right solution, which is good. One caveat here is, of course, that the finite field is not ordered, so we cannot do pivoting right away, or we can do pivoting on non-zero elements, but the default pivoting is on the largest element, so we would need some ordering. So if we are unlocking and having a zero pivot, then the solution will break down for now, just to show you that. So I put the 1, 1 element to a 0, then it's internally converted to the Galois field with base 5, 0, stored in the first element, but then I cannot factorize the matrix anymore. But I plan to hopefully within too long to extend the LU such that it will default not to do no pivoting. Right now it does partial pivoting by default on all floating point values, and it does no pivoting on all the rest. So what I would like to do is to do pivoting on non-zero elements. So it just picks the first non-zero element, do pivoting, and then we'll be able to get a solution whenever the matrix has full rank. Yeah. So here, just to sketch what is the cost, because typically you can do things like this in other languages as well, but there can be quite a significant overhead for constructing user-defined types. In Julia, the distinction between built-in types and user-defined types is not that big. It's actually almost not there. The built-ins are written in Julia, most of them, and you can see, for instance, how they, if you look into the source, where they are defined. So if I compare here multiplication of a matrix a little bit larger to actually have some numbers that are not just 0, integer matrices, and multiply these new matrices with the elements from the Galois field, then the difference in timing is, what is this? This is a factor of 10. And that is mainly, I think, because of the modulus operation that is necessary when we are calculating the, when we are constructing the new results. Our modulus operation could maybe in the future be a little bit faster than it is now. We are trying to be a little bit safe. And also solving linear systems of equations is approximately, what is that also, a factor of 10 slower compared to solving in floating point arithmetic. So it's not a complete different world in terms of timings. Let's see. I think I'll skip the quaternions example, but you can calculate eigenvalues of a quaternion matrix and go to this symbolic case here. So another library that we can call is SymPy. So thanks to Stephen Johnson of MIT Mathematics, we are able to call into Python in a quite convenient way. And because of that, there's been a wrapper of some of SymPy. But the funny thing here is that we are using our generic linear algebra around the basic symbolic operations defined in SymPy. So we are partly using the generic linear algebra in Julia and the functionality of SymPy. So we can set up an arrow matrix like this, where the arrays are simply Julia arrays, and then they have these. It has to load here the first time. Here it is. That's a redefinition warning. So now it's loaded. So we have an arrow matrix where the matrix or the array is a Julia construct, and then the elements are these special SymPy elements. And we can calculate the determinant, and it is the Julia determinant. It is actually doing a LU factorization based on our generic LU and then multiplying the diagonals. And then we're using the simplify function from SymPy to simplify the result of this. And we can also try to make a 0. So if we make the 4x4 element 0, as those of you who work with these kind of matrices know, if we put a 0 in one of the diagonal elements of the arrow matrix, then the inverse has this sparse structure as well. And then we can use again the LU and the rest of the multiplication for generically in algebra to get a result here. Of course, it takes a little bit longer because there's quite a few operations, and all operations are more expensive when it's CAS like this. So yeah, the elements can be quite a few different things, and I would like to explore further stuff to put into it. A last thing I would like to mention very briefly about the generic part here is that there's a lot of promotion going on behind the scenes. So because of the way these types of the arrays work, we can quite easily determine what is the minimum type necessary for storing the element. For instance, if we want to do an LU factorization of 2 integer matrices, we cannot do that within the integers. So then we can say, okay, let's instantiate a 0 and a 1 of integers. Let's make a division and see what is the type of this operation. So as it is now in Julia, that will be a floating point value. And then we can say, produce the return array as a floating point array. But if the input is 2 rational numbers, then we'll take a 0 and a 1, instantiate that for rationals. The result will be a rational, and we will make a rational array as a return type. So we are doing that for all the factorizations. So if it's a QR factorization, we need to see, can we scale the input with some square root of the norm of the input vector. That is the operation we need to support to do a QR. So let's figure out what is the element type that is stable under this operation. So because it's the algebraic closure of operation we are trying to do computationally here, to figure out what is actually the necessary promotion for this linear algebra operation. And all our linear algebra operation, or I hope all of them, will do this operation initially to figure out how should I actually store it. So for the functions defined in base, you should rarely get a response that the element type you're trying to use for the operation is not supported. We should just be able to promote to the minimum necessary element type for the given operation, given some rules. Okay, so much about the generic linear algebra. If there are no questions, I'll continue to my section. Julia is fast. And as we saw before when I scrolled down, this is an example of what is actually the assembly behind the addition of 2 floating point numbers in Julia. There's a very convenient macro, so you can take a Julia expression, and in many cases you're able to have Julia just return what is the assembly this compiles into. And it can be handy sometimes if you have a function, say, why is this not as fast as I expect? Then you can have the assembly printed and see what kind of thing is actually going on here. In this case, it's just a floating point add in the XMM registers. But in other cases, I've worked in an example myself where we looked into how many loads and stores are we actually doing from vector, and then you have a very handy way of getting the assembly instead of having to compiling and opening new separate files and so forth. There are also different other representations of the code you can get. You can get the LLVM intermediate representation if you want to look at that kind of stuff, but that's typically not what I'm doing. One important thing for this to work well, so the exercise is basically write to Julia, if you want to have fast code, write to Julia in a way that Julia can translate this into fairly efficient machine code. So the rule here is try to write your functions in a way such that the types of the inputs maps directly, the concrete types of your inputs maps directly to concrete types of output. So let me give an example of where this is not the case. So I'm defining two different functions here, is11 and is12. So I'm taking the input, testing, is it equal to 1? In the first case, I produce true if it is true, or 0 if it's false. So the problem is here that true is a Boolean and 0 is an integer. So here the return type depends on the input value. And that is the thing to avoid if you're writing Julia. That should be fast. So the good thing is it will work. The bad thing is you will have a speed penalty because it will be more demanding for Julia actually to do checks here when the type is not stable. Is usually what we call. In contrast here, the 2 version is either producing true or false, so the result is always a Boolean, and that is just simply faster for Julia to work with. So an example here. This is 009 and this is 0025, so it is a bit slower in this case, and it can be much worse. If you end up with some operation or function internally in an inner loop that has this problem, you can pay quite a significant price. But there are ways to when you get a little bit more experience with Julia, to figure out these kinds of problems. But if you get it right, then Julia is able to produce fairly efficient code. But you can also, as I said, you can just look at the different kinds of codes here, get the assembly of the two cases. So the efficient version here is very compact, and you can see the actually operations and the registers. And you can see here, I think what's revealing the problem is that we have a $sign JL underscore true here, which is not a usual thing you'll see in C in assembly from a C compiler. But there are easier way to usually we'll simply just see that your function is allocating a lot of memory. For instance, that's another indication of some problem with type stability. So does this mean that we can use Julia for numerical libraries? And I hope that, and I think, and would like to see if we can go a bit in that direction. So the first question is BLAS. And I guess you know the result, but the best argument here is Stephen Johnson's notebook here that he's been kind enough to let me use. So where he's generally treating different kind of matrix multiplication. So it's a very naive 3 nested for loops, what you would do immediately if you just wanted to multiply some matrices, and then adding a more sophisticated recursive matrix multiplication method that actually is nicer to the cache. So, and then he compares that to our BLAS library, which is a very optimized library that's called OpenBLAS, as some of you might know. So here first he compares a naive algorithm with BLAS and sees that it falls off the cliff here because you the cache is really not used efficiently after the matrix grows for a while. But then he makes a recursive matrix multiplication method completely written in Julia, which is the black one here, and then he's actually able to keep a fairly decent performance. But the conclusion is, for very fast matrix multiplication, you have to rely on very, very optimized libraries. So probably and furthermore, I should say here, Julia is single-threaded, so you get the multi-thread by using BLAS. So we'll not see a Julia BLAS very soon, if ever. But that said, there is other libraries than BLAS. So for instance, what about LAPACK? So the point in LAPACK to a large extent is to exploit BLAS. Do blocked operations and then rely on BLAS being able to do the kernels in a fast way. So can we write a block Cholesky in pure Julia except for the BLAS calls? So the same philosophy of LAPACK, but purely implemented in Julia. So this is a block Cholesky. So we just have to decide on these block sizes here and then put it into these different kinds of BLAS calls. And then let me show the result of how this could look like performance-wise in Julia. So I have an experimental package where I have implemented a block Cholesky, which is based purely on Julia plus BLAS. So, and it is the one that is called with this fairly long name here because of the namespace. And compare that to our basic Chol, which is the LAPACK Cholesky. So what I'm saying here is that actually my version here for this 2000 by 2000 positive definite case here, real positive definite case, the pure Julia version is actually faster. And that was, I expected them to be approximately equally fast, but actually the Julia version happens to be faster here. So the overhead of using the high level language here is non-existent. So at the level of LAPACK, I think we could actually get a long way. So if you're careful and write your code in a way that makes the output type determined by the input type, then it's actually possible to get very, very fast code in Julia. Another example is this. Oh, I should say, I was a bit puzzled by why the Julia version was actually faster. But one reason for this could be that, and I'm guessing now, the block size in LAPACK is fixed at compile time. And then it says in the LAPACK manual you should try to fine-tune this blocking size. And I don't think many of you are actually doing that and recompiling LAPACK. So my point here is that here it's fairly easy because in my version down here, I'm simply supplying it as an input argument. So if you want to, you can just loop through the different blocking sizes and you can try for your machine, hopefully very soon, to get a graph showing you what is the performance as a function of the different blocking size. So it will, with some noise here. So here you have the size of the blocks you're using for BLAS calls, and then you're having the running time on the first axis. And I think the default in NetLab LAPACK is using a 64 block size, which seems to be reasonably in this case here. So I think it's matter of luck that mine is slightly faster. But just saying, these things that are hard-coded into LAPACK and these kind of libraries and that we just keep hidden away and will never change, it might not have to be the case because we can actually write code that is easier to read and easier to modify in Julia. Sorry about that. Next example of this is the symmetric tridiagonal eigensolver, which is a problem that doesn't need any BLAS calls at all. So here it is you cannot really benefit from any BLAS3 calls, and I have made my own implementation of the same algorithm, which is a square root free algorithm that LAPACK uses for the eigenvalues when you don't request the vectors. And in that case, it actually also happens that it is faster for some reason. So I want to suggest that we can get some way by writing libraries at that level, exploiting BLAS whenever possible in Julia. Yeah?
So the eigenvalues are different up to which one's more accurate?
A fair case could be that LAPACK is more accurate than mine.
So is this because the LAPACK is actually trying to spend more effort to get more accurate solutions? That's why it's more.
I think it is more accurate because there's gone quite much effort into it. It's the same algorithm, but I might have been making some small, unfortunate decisions in my implementation. So if anyone out there, but that being said, this is for all eigenvalues types. Some of them are fairly small, so maybe some of you know better than me what is actually to be expected. But then some of the eigenvalues will be in addition, so there will be some error in the eigenvalues. So one of the benefits of this is that I can just use arbitrary precision arithmetic to see if the error is different. So I made this problem smaller because it's more heavy, but if now I'm using arbitrary precision and the error is of order 10 to the power of minus 13, And if I'm changing to use float 64, it is about the same. So I don't have any reason to believe that I'm making large errors at least. Because if I use arbitrary precision arithmetic, then the error is not really larger in my implementation.
It's probably a silly comment, but I don't think your eigenvalues are that off because you have a random matrix, the eigenvalues are large, and then you norm it, so you look at there's 2,000 of them, and so I think we get.
I just scaled it down because of the arbitrary. The first example was 2,000.
That's consistent. I thought you would get. That's error precision.
Yeah.
Okay, so the code that's written in LAPACK has been tested on like huge sets of examples to see if it breaks. And you've just written something up in running a random matrix until you actually validate it by running on millions of examples. You don't know that you really have to put out.
No. I'm not saying that. What I'm trying to say is that I think you have the option of writing algorithms like this in Julia. I'm not saying that my algorithm at all can compete with the LAPACK algorithm. They have been tested for so long. Just saying that Julia is probably a language where you can write such algorithms.
Yeah. Because it's just fastest.
Yeah, exactly. I don't think you should substitute LAPACK with my code yet. So, but I.
Over time.
Yeah.
Not that it's your fault. There were a lot of questions.
Then I will actually think I'll stop here. Just with the closing comment that we have some work to do on parallel stuff to make it really competitive. So, and we are doing that now. So, sorry for missing the time. So, yeah.
Is there another talk on Julia next week, and what's the subject for that?
The talk will be Ousterhout, so maybe you can.
Yes, I'd love to complement this. We've been doing some work with Finite Fields to work on computational random matrix theory. So I thought I'd introduce some of what we've been doing, which is sort of the random complement to this talk.
And there's going to be also some kind of discussion on the internal architecture of the software.
We can try to answer questions that you may have.
Everybody's here. Well, Andreas is leaving soon, but Jake and Jihao, I'm sure, would be happy to discuss for the entire next week.
For supercomputers, NPI plus Julia is an obvious idea, but you have a good idea.
It is being very much explored. I'm not sure I have to do it here, but I can say that people are really working on this. And last month, people were running Julia on a crane, a large crane in Switzerland, and Intel CEO looking into what we can get out of Julia on supercomputers. So people are looking into this, but it is very much an open question how to exactly do it. You can we have read some MBI, you can call MBI from Julia, but it's not at all as settled. Yeah.
Automation is about functioning as fast in Julia. Do we have any comment on the data? That they are
I don't think. I don't think I can say anything in general about that. Because I won't try to answer that question. So, but it could be tested. Yeah.
Is the emphasis on linear algebra? You've talked about linear algebra, but there's there's graph algorithms that are very important. Is that part of Julia too, and you're just only discussing it?
My focus here is on linear algebra is very much because that's the thing I've been doing, but people are doing a lot of graph stuff, but it's not something that I have spent much time on. Yeah, but people are doing that, definitely.
So actually, Jihal is one of the people doing this. So by the time he leaves next week, we're hoping to have an algorithm for graph visualization that uses a distributed sparsely square solver to do something that's maybe a little bit more stable than the usual force-directed layout that we can have in Julia.
So the Julia inherited one thing from MATLAB, which is that arrays are fundamental, it seems. Whereas my understanding of Python or JavaScript, it's associative arrays that are fundamental. Are you with me on this difference?
But we have built-in data types in Julia that fully complement any type of higher level, language that you would have. So we have dicts, we have ordered dicts, we have sets, we have arrays is just one type in the whole constellation of user types that people have defined, and they're all first class. That's the important distinction. Is that
therefore, Julia is in no way meant to be scientific.
It is not just purely a scientific programming language. You can write web service in it. You can do it's much more expressive than say like a MATLAB, where running a web server or running a parser would be very, very difficult, right? So it's meant to be more general than just this.
So my favorite example is there's a startup in Somerville, Massachusetts that is using Julia to drive 3D printers. So maybe it gives you an example of like what people are trying to do.
Do you guys claim a speed up over compiled language versions?
You can't claim speed up because it's using Clang's. It uses the same code generation as Clang, for instance. So it only ever